Hello and welcome to the logic of it all. In this video, we will see some applications of tree traversal algorithms introduced in the previous video. Let's start with this example. If you remember from the previous videos, we explored this idea that an arithmetic expression can be written as a binary tree. And usually we call that binary tree the parse tree of that expression. So here we have a binary tree that represents an arithmetic expression that involves A, B, C, and the operators for multiplication, division, subtraction, and addition. Now, we want to see what happens if we apply an in-order traversal on this tree. Okay, so if you remember, for in-order traversal, when you start from the root node, you don't process, here process is writing it down, you don't process the root node, but you go to the left subtree first. So we go to this entire thing. So now we are at this node. We don't process the division yet. We go to its left subtree. So we are here now. We don't process the multiplication yet. We go to its left subtree, and A would be the first thing that we write down. Now that we are done with the left side of the multiplication, we write down the multiplication. Then we go to its right side, and here's B. Now we are completely done with the left side of the division. So after we are done with the left side, then we process the node itself, which is division. Then we go to its right side. So we go to this binary tree on the right side of the division. So now we are at this node. We don't write down the subtraction yet because first we need to go to its left subtree, and there we see a B. Then we go back to the top node, the subtraction. Then we go to the right, C. Now we have finished everything on the left side of the multiplication on the top, so it's time for the multiplication. After that, we go to the right side of the root node. So now we are here looking at this node. We don't write down the addition, the plus sign yet, because first we need to go to its left. So if we go to the left, we see B, and then after that we process the root. For this subtree here, the root is B, and the root is this plus sign, and then we go to the right and C. So this is going to be the result of in-order traversal of this binary tree that represents an arithmetic expression. Now, if you think about it, this is exactly how we write down this expression. We say A times B, so that's A times B, divided by B minus C, so this is B minus C, and then multiplied by B plus C, and here's your B plus C. So if you just fully parenthesize this, we get this expression, which is the normal way that we write down arithmetic expressions. And by the way, that is called infix notation, because we write down the operator in between the two operands, right? So for example, if we are talking about addition, we write down 3 plus 2, so the operator is in the middle. Same with multiplication and division and so on, right? So that's called infix notation. And what we realize here through this example is that if we have the parse tree of an expression and then we do an in-order traversal, what we get is the infix representation or infix notation of that expression. Now, there are two other ways that we can write down arithmetic expressions, namely prefix and postfix notations. So let me explain first of all what is prefix notation. So prefix means that the operator, whatever that is, addition, subtraction, multiplication, and so on, comes before the two numbers. So if you want to write down the sum of 2 and 3, you should write plus 2, 3. So that's the prefix way of writing it down, instead of putting the plus in between, which was infix notation. If you want to write down 7 times 4, you say times of 7 and 4. So the operator comes first, that's why it's called prefix. Now, if you have more than that, so if you have something like, let's say 3 plus 7 times 4. So obviously this is in infix notation, right? Because the multiplication is between the two numbers that we are multiplying, and then the addition is between the two expressions that we are adding. So this is infix. Now if I want to write the same expression in prefix notation, so this is an addition of two terms, so plus comes first, and then the first thing that we are adding is 3, and what we are adding on the other side for plus is this product, so it's a multiplication, so multiplication should come first, then 7 and 4. So this is called the prefix notation. So we have the product of 7 and 4, and then the addition of that product with 3. Okay, so 7 times 4 is 28, and then plus of 3 and 28 is 31. And it turns out that prefix notation and also the next one, postfix notation, in many applications are easier to process in terms of writing a program and so on than the method that we are used to, which is the infix notation. So infix notation is easier for us to see and understand, but if you want to write a program that manipulates these expressions and evaluates them, prefix and postfix notations, depending on the application, can be easier to deal with. So this is the prefix notation, and you can guess what's going to happen now is that if you have the same parse tree for the expression, and this time we do a pre-order traversal, what we are going to get is the prefix notation of that same expression. And if you do that, actually, you'll see that for prefix, remember, we do the root first, so multiply. So that's the first multiplication here. Then we go to the left, we have division, so that's the division here. Then we go to the left again, we have multiplication, so that's the multiplication here. And then we go to the left, we have A, and then we go to the right, we have B, and so on and so forth. So if we do a pre-order traversal of this parse tree, what we get is that expression that we had in the previous slide, but this time in prefix notation. Okay, and sometimes it's called Polish notation as well. And one of the nice things about this is that with prefix notation, you don't need to parenthesize. In infix notation, when you have multiple operations, addition, subtraction, multiplication, to be clear what the expression means, you need to parenthesize it in most cases. But with prefix notation, we don't have to do that. Now, as I said, there is a third notation for these expressions, and this is called postfix. And you can guess what's going to happen here. The idea is that this time the operation comes after the two numbers. So if you want to write down, say, 3 plus 4, you say 3, 4 plus. If you want to write down 2 times 5, you say 2, 5 times, and so on. Now, if you want something more interesting, for example, if you have 3 plus 4 times 7, and obviously, again, this is in infix notation, or a standard way that we write them in mathematics, because here we are adding and the addition is between 3 and 7, and here we are multiplying and the multiplication sign is between the two numbers that are being multiplied. So this is infix, but if you want to write the same thing, the same expression in postfix, it will be 3, 4 are being added and then multiplied by 7. So this is called the postfix notation of that same expression. So you see, we have the addition of 3 and 4, and then the multiplication of 7 with whatever that expression 3 plus 4 is. So that's the postfix notation. And, again, following a similar kind of idea, we have the parse tree. This time we do a post-order traversal, which means left, then right, then the parent. And if we do that, you'll see that we get this expression, which is the postfix notation of that same arithmetic expression. And sometimes this is called the reverse Polish notation. So just to clarify where A, B, and so on come from, we start from the root. We don't process that yet because this is postfix. We go to the left, left again, and then we go to A. So that's the first A here. Then we come back to the root, but we don't process that yet because we have to go right. Remember, postfix says left, right, then the parent. So we go to B and process B. So that's the second thing here. And now that we are done with A and B, we process the root node for those, which is the multiplication, and so on and so forth. Okay, so there is this interesting connection between our traversal algorithms and infix, prefix, and postfix notations for expressions. Another application that I would like to talk about here in terms of using these traversal algorithms is the following. In many cases, when we have when we have some data and we want to store that in a data structure, we use binary trees as our data structure. So the data that you want to store, instead of storing them in an array or a vector or any kind of sequential data structure, we store that in the nodes of a binary tree. Now, how it's done is not the topic of this module here, and in a data structure module that will be discussed in detail. But the idea here is that at every node we have a key. Now, for example, if your application, if your data, the data that you're storing is a phone book, so you have names and corresponding phone numbers. So at each vertex, at each node, we have those two things. We have the name and the phone number for that person, and so on and so forth. Okay, now we're going to call the name the key and the phone number the value, because we call the names key because that's how you look for something based on the names. And then the thing that you're looking for is the number. So we call the phone numbers the values that we want to look up. Now, let's say you have this very small phone book with only 5 names and 5 numbers, and you want to look for the phone number for Mary, right? So one algorithm that you can apply any of the algorithms that we talked about. So for example, you can do in order, right? So you go to the root, you check the name, is it Mary? No. Then you go to the, I'm sorry, you start from the root node. You don't process that yet because I said in order, so I have to visit everything on the left first. So I go to the left subtree, go here. Then now I'm at this node here. I don't process this node yet. I go to its left subtree again because we are doing in order. Now this one doesn't have any left, so it's time to process this. So now in this example, processing is not just writing down the name or the label. Here we are actually performing a search. So we are looking for Mary's phone number. So what we do is we check the name Mary with the name stored here, John, and they don't match, so we move on, right? So we move on means we go now to the root, check the name Mary with the name here. They don't match, so we don't we are not interested in this phone number either. Then we go to the right subtree and we check, we match the name that we are looking for, Mary, with the name stored at that node, and they do match, and we return the phone number at that. Now, what I performed here was an in-order traversal. You can imagine doing post-order or pre-order as well. So you can use this to search a tree, and that tree is a data structure that contains, in this example, names and their corresponding phone numbers. Now, this works, but the problem with this, which will motivate our next move in the next videos, is that the problem is that this is not the most efficient way of doing this, because it could be that depending on the name that you choose and the algorithm that you use, you need to visit most or sometimes all of the nodes before you find the phone number that you're looking for. For example, if you do an in-order traversal and you're looking for Alice's phone number, then you start from here. You don't process this yet. You go here. You don't process this yet. Then you go here. You check John. That's not Alice. Then you go to the root of that or the parent of that, Jane. That's not Alice. Then you go here. Mary. That's not Alice. Then we go to the root, Bob. That's not Alice. And finally, we go to right because that's the way that in order works, and we find the phone number for Alice. So we visited all the vertices before our search concluded. So this is not good, because imagine your phone number having thousands of numbers. Your data structure can be very very large, and this is not an optimal way of searching it. So in the worst case, as I said, you may need to visit all the vertices before you find the one that you're looking for. And that will be the motivation for what's called a binary search tree that we'll introduce in the later videos. And let's finish this video by looking at the algorithm that does exactly what I explained. So this is the pre-order version. So it searches for the name n, which is a string, and the 3T is our actual binary tree that contains all the names and their phone numbers, right? So you initialize the phone number to the empty string, then you match, because we are doing pre-order, right? So you first do the root node, which means you match the name that you're looking for with the name at the root. If they do match, then you make the phone number to be the phone number stored at the root and you return it. Otherwise, you go to the left subtree and recursively do the same thing. And if you don't find it there, then you go to the right subtree and you make a recursive call there. So these are your two recursive calls, right? So there you have it. But as I said, this is not the best way of doing this, because it may take you through all the vertices or most of them before you actually find what you're looking for. In later videos, we will talk about binary search trees, where this can be made more efficient.